Welcome to the Explainer. It's funny. Have you ever stopped to think about how something as simple as counting, something we learn as kids, could possibly be connected to something as vast and complicated as the entire internet? Well, today we're going to build a mathematical toolkit piece by piece and trace that exact path.
I know, it seems like a massive leap, doesn't it? Going from some fruit to the global network. But honestly, it's a journey we can follow just by adding one concept, one tool at a time. We're going to start with the very first idea we ever learn and end up with the mathematics of connection itself.
And it all begins right here, with numbers. The first thing we learn to do with them is just count things. So let's say you've got 20 mangoes, and you want to share them with 5 friends. Numbers are the tool that lets you even begin to think about that problem. So, yeah, on the surface, it's just a simple division problem, right? 20 divided by 5 is 4. But what are we really doing here? If you think about it, you're just doing subtraction over and over. You hand out 5 mangoes, then 5 more, then 5 more, and one last time. 4 steps. It's the same result, but seeing it this way shows you the actual logic, the engine running underneath that division sign. Okay, but as problems get more and more complex, just having a big, messy pile of numbers isn't going to cut it. It's not very useful. We need our next tool, something that'll let us bring some order to the chaos and create specific, meaningful collections. And that tool is the set. A set is just a way to bundle things together. It could be a set of your friends, a set of those mangoes, or something more abstract, like, say, the set of all even numbers. And the cool thing is, we can build these sets with incredible precision. There's this powerful idea called set comprehension. Just think of it like a bouncer at a club. You start with this huge crowd outside. That's our universe of all integers. Then you give the bouncer a very specific rule. Hey, only let in the even numbers. The set is just everyone who makes it past the rope. Simple as that. And once we have this idea of sets, we can start to see this really beautiful, nested structure inside our whole number system. The natural numbers we count with, they live inside the integers, which also include all the negative numbers. And the integers, they live inside the rational numbers, fractions, and all of those live inside this huge, expansive set of real numbers. It's like a set of Russian dolls. All right, so we've got our collections, our sets. That's a great start. But what happens between these sets? How do they interact? We need a way to lay down the rules of the game. And for that, we're going to need our next tool. And here it is, the function. The best way to think about a function is like a perfectly reliable machine. You put a valid input in one side, and you are absolutely guaranteed to get one and only one specific output. No guesswork, you put a 2 into the square function, you get a 4. Every single time. Now, functions are amazing for these kinds of static, predictable rules. But let's be honest, our world isn't static at all, is it? It's always in motion. When you throw a ball, it follows a smooth curve, not a bunch of separate, fixed points. To describe that kind of thing, we need a much more dynamic tool. And that tool is calculus. This is the mathematics of continuous change. It's what allows us to go from looking at a flipbook of still images to watching a smooth, flowing movie. It lets us analyze things as they're actually happening, in real time. The engine that drives all of calculus is this idea of the limit. Imagine you're walking towards a wall. A limit doesn't care about what happens when you actually smack into the wall. It asks a different question. What is the exact spot on that wall that you are getting infinitely, ridiculously closer to? It's a mind-bending idea, but it's what lets us zoom in on one perfect single instant in time. So, how do you figure out some of these really tricky limits? Well, one of the most clever and honestly beautiful tools is something called the sandwich principle. The idea is so simple. If you have some messy, complicated function that's literally sandwiched between 2 much simpler functions, and you know that those 2 outer functions are both heading to the exact same destination, well, where else can the middle one go? It has no choice but to go there too. It's trapped. So this concept of limits, it unlocks 2 incredible, almost opposite superpowers. On one side, you've got differentiation. That's like pulling out a super-powered magnifying glass to zoom in on one single point of a curve and find out exactly how steep it is at that one instant. It's how your GPS knows your car's speed right now. Then on the other side, you have integration. That's like adding up an infinite number of unimaginably tiny slivers under that curve to find the total area. It's how you take all those instant speeds and figure out the total distance you've traveled on your trip. 2 sides of the same coin. Okay, it's time for the final tool in our toolkit. And this is the one that really brings it all together. It takes all these ideas we've been building and uses them to model the complex, interconnected systems that are literally all around us.
We're talking about graph theory. Now, don't let the name fool you. This has nothing to do with bar charts or pie graphs. This is the mathematics of networks. It's all about points, or nodes, and the lines or relationships that connect them.
And this is a perfect illustration of why graph theory is so powerful. Look at this. You can take a messy, real-world problem, like how do you color a map so that no two states sharing a border are the same color? And you can just strip away all the extra stuff, the geography, the weird shapes, and boil it down to its essential information. Each state becomes a dot, a node, and you just draw a line, an edge, between any two states that touch. Suddenly, the problem is so much clearer and easier to solve. And this incredibly simple model of nodes and edges, well, it's unbelievably versatile. It can be your friends on social media. It can be all the routers and computers that make up the internet. It can be airline routes connecting cities. It can even be your class schedule, showing you which classes you can't take at the same time. It's basically a universal language for describing connections. And there you have it. That's our toolkit. We started out just counting mangoes. From there, we learned to group things into sets, we defined rules with functions, we analyzed change itself with calculus, and then finally, we mapped entire networks with graph theory. Each tool built right on top of the last one, giving us a more and more powerful lens to understand the world. So when you realize that everything from your friendships to the global economy can be seen as a graph, it really makes you wonder, right? What other connections are out there, just waiting for us to discover them?